Welcome to this session on Virtualizing Spark. I'm going to talk for about 25, 30 minutes or so. We'll save the questions to the end so as I can get through the material. But you're welcome to ask me questions either in the last 5 minutes or afterwards. Or raise your hands during the session and I'll remember you from that. So we're going to talk here about placing Spark into virtual machines. And why would you do that would be the first question that most people would ask. And if you think about all the cloud work that's going on now, all the work on AWS and Azure and Google Cloud, those are not running bare physical machines, they're running on virtual machines. So the question, why virtualize Spark, has really largely been answered. But what's new in this talk is virtualizing Spark in the same way on premises as you would do in the cloud. And I'm going to show you how those two relate to each other. So why virtualize Spark? I'll spend very little time on that, give you some use cases that we've come across in about 5 years of working on Hadoop and Spark in general on VMware. I come from the core vSphere unit at VMware, the core hypervisor that sits on the bare metal and behaves like an operating system, but it's running virtual machines instead of processes. So that's the core vSphere business unit. So I'll do a quick review of the architectures, the Spark architecture, the Hadoop architecture, the Yarn architecture, and show you how these things fit into virtual machines on vSphere. And it's very simple. Everything that you would put in a physical machine on a Yarn system goes into a virtual machine. Everything that would be a Spark worker goes into a virtual machine. Everything that would be a Spark driver goes into a virtual machine. Very simple virtualization. So I installed all that by hand, actually, when I was installing Spark on my virtual machines, and I've done that at least 20 or 30 times in the last 6 months or so. So if I can do it, anybody can do it. It's a very quick process. What does Spark when it's virtualized look like? And then virtualizing Spark in the private cloud on premises, which some of our customers insist they still want to do, and we're happy to do that with them, but also in the public cloud, using the same infrastructure. That's the new part in this talk here. And then VMware Cloud on AWS is VMware vSphere running on machines that happen to be owned and managed by AWS at their data centers. This is not running on top of EC2. This is running bare metal VMware hypervisor on the metal, on the hardware, at an Amazon data center. And this is a relatively new service from VMware, has been out about a year now, customers already using it, and I'm running Spark on that here in this talk. And finally, everybody's obsessed with performance. If I virtualize, won't I slow myself down? The answer is no. You'll actually equal, if not better than, native performance if you follow the best practices that I'm going to give you here. So why virtualize Spark? Well, enterprises have lots of different flavors of Spark and lots of different sizes of clusters and lots of different vendors, actually. Whether you get your Spark from Hortonworks, from Cloudera, from MapR, from Databricks, from open source Apache, you're probably in the multiple version, multiple vendor world. You're definitely in the multiple version world. And so you need to run these clusters together. You need to run cluster at version 2.2, version 2.3 of Spark, perhaps even Cloudera version 5.12, Hortonworks version 2.7, all at the same time. How are you going to do that? Each of these clusters looks in the old world like a physical cluster. Virtualization is the answer to that problem, clearly. Organizations need different versions of Spark to be available to different teams for different purposes. You may have a data science team, an analytics team, an ATL team, all with their own different clusters. And giving them physical hardware to do that is really the old-fashioned way to do it. Enterprises no longer that we meet, no longer want to dedicate a full set of hardware to just one cluster. And I know many of you are running in the cloud. You don't even think of sets of hardware anymore. But these same principles I'm going to use in the cloud in a few minutes here. So if we look at a classic Yarn architecture, we've got the resource manager scheduling all the jobs on top here. That's this guy on the top. And we've got the name node running all the HDFS files. And we've got a bunch of workers here. Now, how do you virtualize that? Well, it's very simple. You put it into these red boxes, which I'm going to call instances or virtual machines. Those happen to be placed on servers somewhere in your data center or in the cloud, and that's all there's to it. You don't change the yarn architecture because you virtualize it in the slightest bit. Maybe you treat the two topmost virtual machines with a little more care and attention than you treat each of the workers, because you'd really like your name node to live for a long time and not be interfered with by anybody else. You might do the same for your resource manager, but the workers are really commodities. They can come and go as you please. If one of these virtual machines dies, we can replace it with a new one, and the cluster still goes on working. Now with Spark, we have taken out HDFS. We've taken out all considerations of storage, and we're focused mainly on the compute side. And this is a big advantage in terms of virtualization, because you can do your storage on NFS, do your storage on HDFS, do your storage on S3, and the compute that makes up Spark doesn't care about it. It can work with all of those. And the same is true in virtualizing. So you're going to see me virtualizing this later on and pointing it to S3 for the data, or pointing it to EBS for the data, or pointing it to an in-house NFS, but not changing the application logic in any significant way. So that's virtualizing Spark. That takes each of these components and puts it in a virtual machine. And I'm going to do that now. Here's that same diagram turned on its side, where each of the worker nodes is now a virtual machine rather than a physical one, and the driver is a virtual machine rather than a physical one, and the architecture is exactly the same. And if, by the way, I were using HDFS here, and therefore direct attached storage, that would work exactly the same on vSphere as it would on physical machines. So no real change to the architecture of Spark, or Yarn, or Hadoop, no matter how I decide to virtualize it. So this is just another picture of Spark running on top of Yarn. This time the driver is inside the application master component of Yarn, and the executors are running as containers inside Yarn. How many people in the room here are running Yarn underneath Spark? Some people are, maybe 20%. How many people are running Spark standalone? No Yarn in the picture? About the same number of people. So the audience breaks up 50-50 there. How many people are running Spark from a vendor of any kind as opposed to open source? About a third of the audience are running Spark from a vendor. So many of us, like me, are running Spark from open source as well. Standalone Spark is perfectly adequate to run on VMware, just as it is on on-premise hardware. So now, running Spark in the private cloud and public cloud. How could I do this? And we're all familiar because we're at this Databricks conference with running Spark in the public cloud, but I'm going to show you another way of running in the public cloud that actually matches up to how you could run it in the private cloud in a one-on-one fashion. So taking a virtual machine from my on-premise data center, running Spark, and placing it down onto my off-premise, my cloud data center, without changing it, and indeed migrating it live if I wanted to do that. That's what we're talking about in this section, using the same infrastructure. So again, the familiar architecture of Spark with driver on the left and worker nodes on the right, workers containing one or more executors, and executors executing one or more tasks. All of this stays exactly the same when we place each of these things into a virtual machine. So the driver program becomes a virtual machine, the worker node becomes one or more to a virtual machine, and then the executors become one or more to a virtual machine as well. So in the private cloud, which I think about as on-premise deployments, that is, I own the hardware. An awful lot of our customers still do this. They own the hardware themselves in their data centers, and they want to run Spark, and maybe Spark on top of Hadoop on there. So all of the best practices I've given you so far apply, but now since Spark is agnostic to the storage, it doesn't have to be HDFS, it doesn't have to be S3, it could be anything like NFS, and this is the most recent testing I've done, is Spark with NFS, which is, in my case, a very fancy NFS served up by Pure Storage's all-flash arrays, so it's very fast. I was able to get very respectable performance out of the TPC-DS benchmark, running Spark on the left-hand side against NFS data, NFS-mounted data. So this separation of compute on the left from data storage on the right, which is a key element of scaling, is possible even with on-premises Spark in this type of design. And I even went so far as to point my Spark cluster at a remote S3 in this case, which is often an AWS data center somewhere. Now that's a little bit of a crazy experiment to do, but Spark can deal with S3, so if your data happened to be out there remotely, you could get that data too. So Spark on NFS, Spark on HDFS, all works fine in virtualized form. Why would you do this? Well, you could do it so that you could share your machine learning data, your training data, which is in the clustered file services at the bottom, among different clusters. So cluster number 1 at the top, they're all on-premises clusters, by the way. They're all private cloud clusters. Cluster number 1 reads the training data from the shared repository and then trains the model and writes the details of the model, stores the model away back into the clustered file system. You're going to see me do this with S3 in the public cloud in a few minutes. Now the other 2 clusters, which might be a staging or a scaling cluster on cluster number 2, and cluster number 3 might be an operations or production cluster, can read the trained model out of the shared storage and apply it to new data that it's never seen before. So this is data sharing across clusters by means of NFS mounts or other techniques for storage independently of the Spark environment. All very feasible, and we've done this in our labs at VMware with Virtualized Spark. As we see, the story about storage is evolving. I borrowed this slide from one of the vendors of Hadoop here. It used to be the case that we purely did backup to cloud storage. We took our data that's in our in-house HDFS and copied it out to S3, for example, for long-term storage, and then read it back in when we wanted to restore it. It was purely a secondary storage mechanism. But as time goes on, the evolution is going from left to right, and we're seeing that now I might even read my input from cloud storage into my application and write my output to HDFS, or even taking it further, I might read my input from cloud storage, and that's a phrase by which I mean either S3 or EBS or some other form of storage. I might read my input and write my output to cloud storage, both, and then just use HDFS for temporary or intermediate data. So this is one concept of the way storage is going in the Spark world. How does that fit now with Virtualized Spark? Well, as well as that, people have recognized that cloud storage such as S3 can provide some latency to you when you're trying to read massive quantities of that data, such as in a machine learning or analytics world. And so various vendors have built caching mechanisms to do quicker reads of that. And there are a variety of these around the place. They might use local SSD storage for caching the data on the way into the application. Having read it once, you don't have to read it twice that way. So that's one thing about S3 that we're going to use in our virtualization technique now, where we're going to put all of the Spark into virtual machines running on vSphere, but the vSphere I'm using is actually on machines on AWS, running bare metal there. And the data is going to be on S3, just like it would be in a classic cloud application. So here's the same architecture again. Here I virtualized all the Spark processes by placing them into 1 or 10 or 20 virtual machines according to the size of my Spark cluster. And on the right-hand side now, I have cloud storage. In this example, I've taken S3, but it could be EBS or other cloud storage mechanisms. And the link across the two is important because I'm going to be feeding many gigabytes of data into my Spark processes from this cloud storage. So the networking between the compute side and the data storage side is important. And I'm going to come back to that point in a second. So VMware Cloud on AWS, just to be totally clear about it, is not running on top of EC2. It's running on machines located at AWS data centers, which are running the VMware stack. VMware includes a hypervisor called vSphere. It includes a storage system called Virtual SAN. It includes a networking system called NSX, and a bunch of controls called vCenter and vRealize that do the management of all that. That entire stack in the center is installed and brought up for you by VMware when you sign up for VMware Cloud on AWS. It's effectively the VMware stack of software running on AWS hardware. AWS manages the hardware servers, VMware manages the software from the hypervisor up. And then your job as a user is to create virtual machines and put Spark into them once you've done that. And you will see a demo of that downstairs at the VMware booth if you're interested, Spark running in virtual machines. Now, you'll notice, though, that it's very close physically to EC2 and S3. They're in the same data center. So remember, I mentioned the networking a few seconds ago. We're going to use the Amazon backbone network to get data in and out of VMs running under vCenter's control here, so that we have the best possible access to the data when we're running in the VMs. And what that looks like, first of all, VMware manages the hypervisor and management components, and AWS manages the physical resources. This is on VMware Cloud on AWS. The customer, yourselves, would manage the VMs, the creation of instances as you know them today, and the customer decides how many VMs to run on any one vSphere box. Typically, customers start off with 4 boxes. No reason you couldn't have 40 boxes or 50 boxes if you wanted to. You could start with 1 if you wanted to. But generally, we start off a customer with 4 servers to use in VMware Cloud on AWS. So then, here's what Spark looks like running inside of this. Spark is running in the VMs on the left, and it's communicating over this compute gateway over to an elastic network interface that lives inside your VPC, your virtual private cloud, in your Amazon installation. Remember, these two are running in the same data center now. The software on the left is the vSphere VMware software. The software on the right is classic Amazon software. And it's reading the S3 data via the VPC endpoint in the middle in red. It's reading it over that network backbone link, a VPC endpoint, down into the virtual machines there that are running on VMware. And why would I do this? Well, I've already run Spark on premises for a couple of years now. I've decided, or my management has decided, we're going to take that same Spark application and move it up to the public cloud. Or indeed, the reverse of that direction. I have a public cloud implementation of Spark, and I'm going to bring it back in-house for whatever reason. Maybe the data is too expensive to load up all the time, or it's IoT data that has to live on the factory floor, and I need the Spark processing to be in-house. So this represents then the cloud version of vSphere exactly parallel to the private version that would be running on premises. And that networking is the best you can get there as far as speed is concerned. And we've run this for many months now at VMware, running Spark, reading S3 data, and writing S3 data to do machine learning, to do deep learning, to do a variety of analytics on here as well. So in parallel with the previous approach, now we have 3 clusters, one of which is on-premise, the bottom left-hand side one. But the training cluster on the top left, cluster number 1, is reading the training data from S3 and then storing the trained model back into S3 for other people to use. Then the testing cluster, that's the application cluster 2 on the top, right-hand side, is reading the trained model and executing that trained model against test data. Remember the golden rule of machine learning, 70% of your data is for training, 20% is for testing, and 10% is for more testing. So that's the testing phase there where you're operating your trained model against data that it's never seen before to see if it comes up with reasonable results. Having done all that, you then take your trained model again out of S3 into cluster number 3 on the bottom left-hand side, which is your operations data. You're running a factory. You've trained your model to recognize sensor data, data that's coming from sensors attached to your machines in your factory. And you now wish to spot any odd events that are happening with your sensors, any misreads or bad data that's coming in your sensors. And we built an application to do exactly that, to take IoT streaming data and execute a trained ML model against it, a logistic regression model, and that you can get for free from us on GitHub. It's called the IoT Analytics Benchmark suite of programs, and it operates in exactly this way. Now, many of you are thinking to yourselves, I use containers. I use Docker containers for my deployment of Spark or my deployment of Hadoop or my deployment of my analytics application. How can I use containers, and what does vSphere have to do with containers? So down the left-hand side here, the top 2 entries are 2 physical machines, and then everything that has a little green arrow against it is a virtual machine. What you're looking at here is the vSphere client, the vCenter client, the browser-based access to the management tool for VMware. And each of those things labeled W1, W2, W3, W4, W5 are small virtual machines executing a stripped-down version of Linux, which we call the Photon OS. You can see that right here, Photon Container OS. So every one of these virtual machines was generated in the first place by means of a Docker create command. That Docker create command was supplied to something called VMware Integrated Containers. VMware Integrated Containers is a translator of Docker commands to virtual machine instructions. So whenever you create a Docker container in this world, what you actually get is a stripped down virtual machine, one-to-one. And these virtual machines don't contain any Docker code. They contain the jar file for Spark, to execute Spark. So these are Spark worker virtual machines, which were generated to represent containers. They are Docker containers, as far as Docker is concerned, but they're miniature VMs, which are stripped down in their Linux to almost nothing. So this engine that created all this Vic Spark engine here, is something that we call VMware Integrated Containers. So here you see a one-to-one match of container to virtual machine. Now, this isn't the only model. You can have multiple containers to a virtual machine, but this is the simplest one for illustration purposes here. So the moral of my story here is that we don't see virtual machines as competing with containers. We see the two as complementary, either one container to one virtual machine or many containers to one virtual machine. These two can be used together. It's a level of separation that's different. These virtual machines are very much independent of each other. If one dies, or if the container host dies, they don't all go away with it. If one has a rogue piece of malware in it, it's protected from the other by virtual machine technologies. So finally, performance then. Well, I'll give you the results rather than the great details which you can read in our white papers about how this was done. I want you to concentrate on the gold bars versus the gray bars. The gold bars are virtualized systems with 4 virtual machines per host, and the gray bars are the same hardware, but now running just one instance of a Spark worker. So in these cases, you have 4 instances of the Spark worker because you have 4 virtual machines. And this happens to be random forest, but I also have the same results for logistic regression as well. And in each of these cases, with 1 terabyte, 2 terabytes, and 3 terabytes, and we've actually tested many terabytes more than this, in each of these 3 cases, you can see that the completion time, where smaller is better, is lower than bare metal in each case. So we've done this test over and over again with different forms of Hadoop, with Cloudera's Hadoop, with Hortonworks' Hadoop, with Spark, Apache Spark, with Spark running on Cloudera, This test has been run for at least 4 years, or to 5 years that I know of, and the engineer who did that is on our booth downstairs. So this, to me, is evidence that virtualizing doesn't actually take away bare metal performance at all. In fact, it's slightly better, and I'll give you the reason why it's better in a second. Using a different benchmark now, using logistic regression as an algorithm, we were able to show that 4 virtual machines per host came in at about 10% faster than the bare metal equivalent. And the reason for that, everybody asks, why is that? The reason for it is more respect for the NUMA boundaries of the hardware when you break things up into smaller virtual machines than physical Linux pays attention to your NUMA. NUMA means non-uniform memory architecture, which is effectively a segmenting of the memory of your machine to make it local to one or other of the processors on that machine. So a picture of that should be next. So here's a classic piece of hardware now, and I know this is a Spark conference, but we're going to talk about hardware here for a second. So this is the NUMA memory associated with this socket or this processor, and this is the NUMA memory associated with the second processor. And all x86 machines work this way today. All have roughly 2 sockets and all have their own NUMA assigned to them. Now, when you put the blue layer, VMware, on here, that's the VMware hypervisor that is controlling the hardware and giving you a runtime for your virtual machines. Now, let's say you had 1 terabyte of memory on that server. What would be the ideal virtual machine size to put on that server? And VMware understands how to do this, and those results that I showed you came from this best practice that I'm going through with you here. So each NUMA node has 1 terabyte divided by 2, which is about 512 gigabytes per NUMA node, roughly, if you have 2 sockets. We're going to subtract a little bit of that memory away for VMware's hypervisor to use. That's this layer here. About 5% of the total memory will go to VMware. And then the remainder goes to each VM. So it's not unheard of to have a VM that's close to half a terabyte in memory size. Perfectly acceptable. We've run virtual machines that are 4 terabytes in size. But as a best practice, on this box, I would put either 2 virtual machines represented by these things, or 4. But if I had 4 virtual machines, I would divide this memory by 2 again. And that would allow me to put 2 virtual machines into this processor's memory, and 2 virtual machines into this processor's memory, and fit them exactly right so that spanning the NUMA boundaries will incur no overhead. When we looked at these NUMA boundaries and saw how much overhead is caused by that, it was somewhere in the range of 15 to 20% overhead. So that's why we're doing better than physical in our performance tests that you saw earlier. So it's time to finish. What you get by virtualizing, you know about already from your cloud experiences. What this is that same cloud experience now on premises, using your on-premises hardware. And the benefits are infrastructure on demand, the ability to give people a Spark cluster when they ask for it. Spin up virtual machines is much faster than purchasing new hardware. Being able to share physical resources among different teams, data science team 1, data science team 2, analytics team 3, that type of sharing. Being able to manage them in a simplified fashion. You saw me managing containers using exactly the same tool set as I manage VMs. And you saw me managing public cloud using exactly the same toolkit as private cloud. That is magic to a lot of our customers. They want to be able to, in the same pane of glass, see their private cloud and public cloud VMs unified together into one management environment. There is resource pools in VMware, which allow me to segment one group of people away from another group and allow them to not interfere with each other, even though they're living on the same hardware. That's called a resource pool, and that gives me cluster consolidation. So testing, staging, pre-production, sizing, all of that stuff goes onto one cluster of hardware. And as you saw, we can do as well as and better than native Hadoop or native Spark in that case, and no significant overhead. And there's lots of white papers on that. If you want these white papers, send me an email. My email is jmurray@vmware.com, and I'll get those white papers to you. And one more thing, I talked about on-premise virtualization and VMware Cloud on AWS, which is virtualization operating in an Amazon data center controlled by vSphere. Thank you very much.